There is a law written into the fabric of the cosmos, a rule so consistently observed that it has become an unspoken truth. It governs the silent dance of particles and the majestic spin of worlds. It is a principle of duality, of an unbreakable cosmic contract binding north to south. You have felt its power every time you snap a magnet to a refrigerator door, a small everyday miracle of invisible force. You have trusted it every time you followed a compass needle, letting it align with the colossal magnetic field of our own planet. This law declares with unwavering authority that magnetism is a partnership, an inseparable partnership. Take the simplest bar magnet you can imagine. It possesses a north pole and a south pole, two ends of a single entity. Now, in a fit of curiosity, break it in half. You might expect to isolate a purely north piece and a purely south piece. But the universe denies this simple request. In that instant of fracture, two new complete magnets are born from the fragments of the old one. Each piece, no matter how small, instantly sprouts its own opposite pole, a phantom limb of force appearing from nothingness. Cleave it again, and again the law asserts itself. Grind it down to a fine dust, and each microscopic grain will be a perfect miniature dipole, a tiny compass needle forever tethered to its other half. From the scale of atoms to the churning iron heart of the earth, this rule holds. North cannot exist without south. South cannot exist without north. They are two faces of a single coin, eternally bound. It's a principle so foundational, so deeply embedded in our physical reality, that we rarely stop to question its sheer, baffling strangeness. A cosmic decree without appeal. For millennia we simply accepted it. It was the nature of the lodestone, the way of the world. Yet lurking in the very same theories that describe this rigid duality is a ghost, a tantalizing hint of a profound asymmetry at the heart of existence. To find it, we must turn to magnetism's sibling force, the architect of our modern world, electricity. Here, the universe seems to play by an entirely different set of rules. We see positive charges and negative charges, the electrical equivalents of north and south. We have the proton, a vessel of pure positive charge, and the electron, its negative counterpart. But unlike their magnetic cousins, these charges are gloriously independent. We can and do separate them with ease. We tear electrons away from their atoms every second of every day. The simple act of shuffling your feet across a carpet is an act of charge separation, of creating a surplus of electrons on your body, leaving a deficit behind. The resulting spark that jumps from your finger is the universe correcting that imbalance. Our entire technological civilization is built upon this fundamental freedom. We create vast rivers of isolated electrons flowing through wires as current. We build up enormous positive and negative potentials in batteries and capacitors, storing energy in their separation. Electricity, it seems, loves solitude. It allows for monopoles of charge. An electron is a pure south of electricity. A proton is a pure north. They can and do exist alone, wandering the cosmos as solitary entities. So we are left with a cosmic riddle, a jarring inconsistency in the book of nature. Why this stark difference? Why does electricity permit these lonely wanderers, these fundamental units of charge, while magnetism enforces a strict, unbreakable partnership? The forces are so deeply intertwined, so fundamentally connected, that they are often spoken of in a single breath. Electromagnetism. They are two aspects of one underlying phenomenon. Yet one side of the equation is populated by individual actors, while the other seems to be a world of inseparable pairs. It is as if we discovered a world where every living creature was a conjoined twin, a biological law with no exceptions. The existence of a single, freely walking individual would not just be a curiosity. It would force a complete re-evaluation of everything we thought we knew about life itself. This deep question was elegantly, almost poetically codified in the 19th century by the brilliant Scottish physicist James Clerk Maxwell. He was the great unifier, the man who took the disparate, messy observations of electricity and magnetism, static cling lightning compass needles and currents, and wove them into a single breathtakingly beautiful mathematical tapestry. His four equations are to a physicist what a Beethoven symphony is to a musician. They describe the behavior of light radio waves and all forms of electromagnetic radiation with near-perfect precision. They are the bedrock of our understanding of the modern world. And nestled within their elegant calculus is a stark mathematical declaration of this asymmetry. 3 of his equations show a beautiful, near-perfect symmetry between electric and magnetic fields. They mirror each other, a change in one creating a dance in the other. This interplay is what allows an electromagnetic wave light itself to propagate through the empty vacuum of space, a self-perpetuating ripple of energy. But one equation stands apart. It's Gauss's law for magnetism. In simple terms, it states that if you draw any closed surface in the universe, a sphere, a box, anything at all, the total magnetic flow in and out of that surface must always equal 0. What this means in a more physical sense is that for every North Pole line of force leaving the surface, there must be a South Pole line of force entering it somewhere else. You can never ever trap a lone pole. The equation mathematically forbids it. A corresponding equation for electricity, however, says something completely different. It tells us that the net electric flow out of a surface is directly proportional to the total charge, the number of lonely electrons or protons you have trapped inside. Maxwell's equations in their celebrated form essentially contain a 0, where for the sake of symmetry a 1 might be expected. They work flawlessly. They predict the world we see with stunning accuracy. For decades this was enough. The case seemed closed. The universe was simply built this way, lopsided, asymmetrical, with magnetism forever bound in pairs. The book was written, the laws were set in stone. But science is not about accepting the stone tablets as they are handed down. It is the art of tapping on them, listening for a hollow space, for a hidden crack. It is the art of asking a dangerous question: what if? What if the 0 in Maxwell's equation isn't a fundamental constant of nature, but merely a reflection of our limited experience? What if it's 0 simply because we have never, in all our searching, managed to find the particle that would make it non-zero? What if the magnetic monopole, the lonely north or solitary south, is not a physical impossibility, but merely rare, exceedingly unimaginably rare? This was a question so heretical it could only be posed by a mind comfortable with tearing down the pillars of physics to see what lay beneath. In 1931, that mind belonged to Paul Dirac, a quiet, intensely brilliant theoretical physicist who was one of the principal architects of quantum mechanics. Dirac was not looking for a monopole. He was wrestling with an entirely different and arguably much deeper mystery, the puzzle of quantum charge. In our universe, electric charge is not a smooth, continuous quantity. It comes in discrete, indivisible packets. Every charged particle we have ever discovered carries a charge that is an exact integer multiple of a fundamental unit, the charge of a single electron. An object can have the charge of 1 electron or 2 or 1,000, but never 1.5. It's as if currency only existed in the form of dollar coins with no cents, no dimes, no quarters allowed. Why this strange rigid quantization? There was nothing in the physics of the time that demanded it. It was just another brute fact of the universe, another cosmic rule we had to accept without explanation. It was in the labyrinth of his mathematics, while trying to reconcile quantum theory with special relativity, that Dirac stumbled upon something astonishing. He found that if you assume the existence of just one single magnetic monopole somewhere, anywhere in the entire universe, a profound consequence would ripple back through the laws of physics. Its mere existence, he proved, would mathematically times force, times electric charge to be quantized. The monopole became a theoretical linchpin. Its presence would provide a deep, elegant, and beautiful explanation for why charge comes in discrete packets. The long, unexplained mystery of quantized charge would suddenly have a reason, a cause. The two greatest mysteries of electromagnetism, the absence of magnetic monopoles and the quantization of electric charge, were in Dirac's vision two sides of the same coin. The existence of one would solve the other. This was a revelation of staggering proportions. The magnetic monopole was transformed overnight. It was no longer a mere theoretical curiosity, a plea for mathematical symmetry. It was now a candidate for one of the most fundamental and essential particles in all of creation. Its discovery would not just fill in a missing blank in Maxwell's equations, it would validate one of the most profound predictions in the history of science. It would be like finding a single ancient key that inexplicably unlocks the most heavily fortified, mysterious vault in the world. The connection might not be obvious, but the fact that it works would prove a deep hidden relationship. Dirac's work gave physicists a reason to believe. It gave them a reason to search. The hunt was on, but it would be a search unlike any other in scientific history. We are not looking for a particle that is merely small or fleeting. We are looking for a ghost, a whisper in the grand silence of the cosmos. A fundamental particle predicted over a century ago, a particle whose existence would solve a deep cosmic riddle, yet one that has stubbornly, maddeningly refused to be found. It is a quest that has taken us from the deepest oceans to the highest atmosphere, from smashing particles in colossal accelerators to sifting through the ancient dust of meteorites and moon rocks. We are searching for a point of pure magnetic force, a solitary north or an isolated south adrift in the universe, a particle that would behave like nothing else we have ever encountered. If a magnetic monopole were to pass through a loop of wire, it would induce a unique and unmistakable electrical current, a signature completely different from any conventional magnetic or electric effect. This is the theoretical fingerprint we are hunting for. Imagine a single particle, a relic from the Big Bang, perhaps traveling through interstellar space for billions of years. It feels the pull of galactic magnetic fields, accelerating to incredible speeds along the invisible lines of force that thread through our galaxy. It carries with it a magnetic charge so immense that its interaction with matter would be like a celestial blowtorch, a trail of ionized atoms left in its wake. It would be an emissary from the dawn of time, carrying a secret about the fundamental unity of the universe's forces. Finding it would be more than just a discovery. It would be a revolution. It would open up entirely new avenues of physics, suggesting that the familiar forces we know are but facets of a much grander unified theory, one that existed in the hellish heat of the first moments after the Big Bang. It would force us to rewrite our most fundamental textbooks, to add a new term to the symphony of Maxwell, completing the masterpiece he began. The search for the magnetic monopole is therefore a search for our own origins. It is a quest for a missing piece of the cosmic puzzle, a particle that connects the quantum realm to the grand architecture of the universe. It is a testament to our relentless drive to understand not just the world as it is, but the deeper reasons for why it must be so. And it all begins with that simple, nagging question born from a child's curiosity. What happens if you just keep breaking the magnet? Why is the universe so profoundly elegant in its symmetries, and yet in one crucial aspect so stubbornly, so maddeningly lopsided? You live your life embedded in a sea of invisible forces, a world governed by a delicate and beautiful balance. For every up there is a down, for every action a reaction. This principle of balance, of cosmic parity, is written into the DNA of reality. It is a rule so fundamental that we rarely even think to question it. But what if we told you that at the very heart of the forces that build our world, the forces of electricity and magnetism that power our lives and hold atoms together, there lies a glaring, unexplained exception to this rule, a deep asymmetry hiding in plain sight for centuries, a cosmic loose thread that suggests our understanding of the universe is profoundly, tantalizingly incomplete. To find this cosmic imbalance, you don't need a powerful telescope. You just need to remember the simple joy of playing with a child's toy. Take any magnet, a simple bar of iron ore, or a colorful refrigerator novelty. You know its nature intimately. It possesses two faces, two identities that are eternally bound together. A North Pole reaching out into the void and a South Pole its inseparable partner. They are a package deal, a cosmic duality locked in an unbreakable embrace. Now try to isolate one. Try to capture a North Pole all by itself. You take a blade and you slice that magnet in half, hoping to sever the connection. But what you find is not one pole but two new, smaller magnets. Each half instantly, miraculously sprouts its own opposite pole. The north you are trying to isolate now has a brand new south, and the south you discarded now has a new north. You can grind it down to a fine dust, to microscopic particles of iron, and every single grain, no matter how small, will be a perfect, complete magnet. A perfect dipole. This isn't a limitation of our tools. It appears to be a fundamental law. Nature forbids a magnet with only one pole. They are, it seems, born as twins and destined to die as twins. Now consider its sibling force, electricity. Here the rules seem entirely different. Electric charge also comes in two flavors, which we call positive and negative. They attract and repel with a familiar magnetic-like dance. A proton carries a positive charge, an electron a negative one. They are the yin and yang of the atomic world. But here, the cosmic law of inseparability is completely abandoned. We can, with trivial ease, isolate a single electric charge. You can gather a cloud of electrons, a sea of pure negative charge completely untethered from their positive counterparts. The universe is filled with lone electrical charges wandering free. A single proton, the nucleus of a hydrogen atom, is a solo positive charge. An electron is a solo negative charge. They are fundamental, independent entities. So why this stark difference? Why does electricity permit these lonely wanderers, these fundamental monopoles, while magnetism insists on perfect unbreakable pairs? For a long time this was just seen as a curiosity, a quirk of nature. Electricity and magnetism were two separate phenomena, each with its own peculiar habits. One was the force that made lightning flash and amber crackle. The other was the mysterious power that guided a compass needle. They were cousins, perhaps, but they lived in different houses with different rules. The story of how they were brought together, united under one roof, is the story of one of the greatest intellectual achievements in human history. And it is in the very architecture of that unification that our mystery deepens from a simple curiosity into a profound paradox. The 19th century was an age of furious discovery. Scientists across Europe were wrestling with these strange invisible forces. Men like Hans Christian Ørsted discovered that an electric current could deflect a magnetic compass needle, a shocking revelation. Somehow, a flow of electricity was creating magnetism. Then the brilliant experimentalist Michael Faraday, a man with no formal education but an intuition that bordered on the supernatural, turned the question around. If electricity could create magnetism, could magnetism create electricity? Through painstaking work, he showed that a moving magnet could induce an electric current in a wire. The two forces were not just cousins, they were deeply, intimately entangled. They were two sides of the same coin, a single, unified entity, electromagnetism. But the language to describe this deep connection was missing. The science was a chaotic jumble of disconnected laws, experimental results, and tangled intuitions about lines of force stretching through space. What was needed was a mind capable of seeing the underlying symphony beneath the cacophony of data. What was needed was a poet of mathematics. That poet was James Clerk Maxwell, a Scottish physicist of extraordinary vision. In the 1,860 seconds, he took the entire messy collection of experimental knowledge, the work of Faraday, Ampere, Gauss and others, and set himself the task of translating it into a single coherent mathematical framework. He wasn't just tidying up, he was searching for the deep universal laws from which all these disparate phenomena would naturally emerge. What he produced was a set of just 4 equations. 4 elegant, compact, and astonishingly powerful statements that would forever change the world. To a physicist, Maxwell's equations are more than just formulas. They are a kind of sacred text. They are as fundamental to our understanding of the universe as Shakespeare is to literature or Beethoven is to music. They describe with perfect precision the behavior of electric and magnetic fields. The first equation, Gauss's law for electricity, is a simple statement of origin. It tells us that electric fields are born from electric charges. An electric charge, like a proton, acts like a fountain spraying lines of electric force outwards in all directions. If you have a source, you have a field. Simple, elegant, and perfectly symmetrical. The second equation is its magnetic counterpart, Gauss's law for magnetism. And it is here, in this second line of the cosmic code, that the universe declares its profound asymmetry. The equation states with absolute, unambiguous finality that the net magnetic charge through any closed surface is 0. What this means in plain language is that magnetic field lines never begin or end. They have no source, no fountainhead like an electric charge. They must always loop back on themselves, creating continuous unbroken circuits. A north pole is simply where the lines of force exit a magnet, and a south pole is where they re-enter. They are not sources, merely gateways on an endless journey. This equation is the mathematical embodiment of our simple kitchen table experiment. It is the universe's official decree: there are no magnetic monopoles, no magnetic charges, no sources for the magnetic field. Maxwell didn't invent this rule. He simply wrote down what all of nature and every experiment ever conducted had shown him to be true. He enshrined this observed asymmetry right into the foundations of physics. The final two equations describe the dance, the interplay between the two fields. They show how a changing magnetic field creates an electric field, and this was Maxwell's own brilliant addition: how a changing electric field creates a magnetic field. It was this final piece of the puzzle, a term added for purely mathematical symmetry, that unlocked the theory's greatest secret. Maxwell realized that these two fields, constantly creating and recreating each other, could propagate through space as a self-sustaining wave. He calculated the speed of this wave using only the measured constants of electricity and magnetism from laboratory experiments. The number he got was astounding. It was the speed of light. In that moment, one of the deepest mysteries of existence was solved. Light in all its forms, from the radiant warmth of the sun to the colors of the rainbow, the invisible radio waves that carry our voices, and the X-rays that see through our skin, is an electromagnetic wave. It is a ripple in the unified field that Maxwell had discovered. It was a moment of triumph, a unification of forces so profound that it stands as one of humanity's crowning intellectual achievements. The universe, it seemed, was governed by this perfect, elegant set of laws. And yet that one nagging asymmetry remained, that zero in the second equation. Why did electricity get to have its fundamental particles, its monopoles, while magnetism was denied them? For 50 years, this question lay dormant. The theory was so successful, so powerful, that the asymmetry was accepted as just a fact, a feature of the universe we live in. It was a house with 3 perfectly symmetrical windows and one that was bricked up. Strange perhaps, but the house stood firm. And then the entire foundation of physics was shattered. The dawn of the 20th century brought with it a revolution that ripped up the classical, predictable world of Newton and Maxwell. A strange new reality was being uncovered, a world that operated on rules of probability, uncertainty, and bizarre leaps of logic. This was the world of quantum mechanics, and it was a world that demanded a new kind of prophet, a mind that could think in ways no one had ever thought before. That mind belonged to a young, impossibly brilliant and famously quiet physicist at Cambridge University named Paul Dirac. Dirac was a unique figure in the history of science. He was a man who seemed to channel the language of the universe directly. His colleagues joked that while other physicists struggled to find the right equations to describe their ideas, Dirac would simply discover the equations first and then spend years figuring out what they meant. He was driven by an almost religious faith in mathematical beauty. If an equation was beautiful and elegant, he believed it had to be true, even if it predicted things that seemed utterly impossible, and he had a track record to prove it. In 1928, he formulated an equation to describe the electron that fully merged quantum mechanics with Einstein's theory of special relativity. The equation was a masterpiece. It was beautiful, but it had a strange quirk. It had 2 solutions. One described the familiar negatively charged electron. The other, a negative energy solution, seemed to describe an impossible particle, an electron with positive charge. An anti-electron. No one had ever seen such a thing. The idea was dismissed as a mathematical ghost. But Dirac, trusting the beauty of his mathematics, insisted it must exist. 4 years later, the positron was discovered in cosmic ray experiments, behaving exactly as his equation had predicted. Dirac had unveiled an entire shadow universe of antimatter, not by experiment, but by following the dictates of a beautiful equation. It is with this history, this almost mystical prescience, that we must approach what he did next. In 1931, Dirac turned his attention to that old familiar asymmetry, the bricked-up window in Maxwell's beautiful house. He wasn't trying to find a magnetic monopole. He was wrestling with an entirely different and equally deep quantum mystery, the quantization of electric charge. Why does electric charge only come in discrete identical packets? Every electron in the universe has exactly the same charge. Every proton has exactly the same charge, precisely equal and opposite to the electrons. Charge doesn't come in fractions. You can't have half an electron's worth of charge. It's all or nothing. It comes in integer multiples of a fundamental unit. In the classical world of Maxwell, there was no reason for this. Charge could, in theory, take on any value, but the quantum world insisted otherwise. Dirac, in a stroke of pure genius, decided to conduct a thought experiment. He asked a deceptively simple question. What would happen if a single fundamental particle of electric charge, an electron, were to move in the presence of a single hypothetical particle of magnetic charge? What would happen if an electron met a magnetic monopole? He wasn't assuming they existed. He was just asking, what if he brought the full power of quantum mechanics to bear on this imaginary encounter? As he worked through the complex mathematics, he found something that must have made the hair on his arm stand up. He discovered that for the quantum mechanics to remain consistent, for the mathematics not to break down into nonsense, a very specific condition had to be met. The product of the fundamental electric charge and the fundamental magnetic charge had to be an integer multiple of a fundamental constant of nature. The implication was breathtaking, a logical masterstroke of staggering beauty. Dirac had found a deep hidden connection between electricity and magnetism that even Maxwell had never dreamed of. The very existence of just one magnetic monopole somewhere, anywhere, in the entire cosmos would be enough to force electric charge to be quantized everywhere. It's like discovering a single massive planet in a distant solar system and realizing its gravity is what locks every moon in your own system into its specific discrete orbit. The monopole was the great cosmic anchor, the unseen regulator. Its existence would provide a beautiful, profound, and purely quantum mechanical reason for why electric charge comes in neat little packages. It would explain one of the deepest, most fundamental known facts about our universe. Suddenly, the search for the magnetic monopole was no longer a matter of simple curiosity or a desire for aesthetic symmetry in our equations. It had become a theoretical imperative. Dirac's 1931 paper transformed the monopole from a missing piece into a cornerstone of our understanding of quantum reality. It suggested that Maxwell's equations were not the final word. They were an incomplete draft, a description of the universe as we happen to see it, a universe strangely devoid of its magnetic charges. The zero in Maxwell's second equation was no longer a statement of fact. It was now the clue to a crime. It was a cosmic question mark. If quantum mechanics is the correct language of the universe, and if electric charge is indeed quantized, which it is, then magnetic monopoles, not only times can times exist, they almost times must times exist. Their existence would heal the ancient asymmetry. It would complete the electromagnetic picture and solve a deep quantum puzzle. The logic was inescapable. The mathematics was beautiful. Paul Dirac, the Oracle of Cambridge, had spoken. And so the great hunt began. A hunt for a particle predicted not by experiment, but by the demand for elegance. A search for a magnet with a single pole. A search that would take us from the deepest oceans to the highest atmosphere, from the debris of particle accelerators to the faint dying echo of the Big Bang itself. The theory demanded their existence. The only remaining problem, the great and enduring mystery, was a simple one. If they must exist, then where are they? And so the equation was no longer just a beautiful piece of mathematics. It had become a map. A treasure map pointing to a phantom particle, a creature of pure theory, whose existence would either confirm a profound symmetry in our universe or leave us haunted by its absence. With Dirac's gauntlet thrown down, the abstract search for understanding became a physical one. The hunt for the magnetic monopole had begun not with grand pronouncements, but with the quiet, determined grit of experimental science. The first generation of monopole hunters knew they were searching for a ghost. They couldn't simply build a detector and wait for it to beep. They had to decide where in this vast and violent cosmos such a singular entity might be found. Their logic was sound, born from the very nature of cosmic violence. If monopoles existed, they would carry an immense magnetic charge, a fundamental stickiness to the electromagnetic field. The universe is threaded with magnetic fields from the tangled webs inside stars to the whisper-thin filaments stretching between galaxies. A monopole moving through these fields would be seized and accelerated to incredible speeds, turned into a cosmic bullet. Our own galaxy's magnetic field would act as a colossal natural particle accelerator, grabbing any wandering monopoles and flinging them across the void. Where then would you look for the impact sites of these bullets? You would look up. You would look to the relentless, unending rain of high-energy particles that constantly bombards our planet's upper atmosphere, the cosmic rays. This was a search conducted at the very edge of our world. Physicists became pioneers of the stratosphere, entrusting their delicate instruments to weather balloons that swelled and rose through the thinning air. They ascended to altitudes where the sky darkens to an indigo twilight. Even at noon, far above the clouds, above the protective blanket of the atmosphere that shields us from this ceaseless celestial bombardment. Here, in this frigid near vacuum, they hoped to catch a particle unlike any other. The challenge was immense. A monopole, if it struck their detectors, would leave a very specific signature. Because of its powerful magnetic charge, it would ionize atoms with an incredible efficiency, like a hot poker searing through tissue. It would carve a path of atomic wreckage far denser and more consistent than any ordinary proton or atomic nucleus. The task was to build a net fine enough to catch this one specific fish in an ocean of cosmic radiation. Early experiments used stacks of photographic emulsion, a primitive but effective technology. These were thick, layered sheets of gelatin containing silver halide crystals, essentially a solid block of photographic film. When a charged particle tore through the stack, it would leave a latent trail, an invisible scar of activated crystals. After the balloon was recovered, often after a long and arduous chase across remote countryside, these emulsions would be developed in a darkroom. Scientists would then spend months, sometimes years, hunched over microscopes, painstakingly scanning the plates millimeter by millimeter. They were searching for a single telltale track, a line of silver grains, impossibly thick, impossibly straight, a perfectly uniform trail of devastation that did not waver or slow down as it passed through the material. It was a manual, exhausting, and often soul-crushing process, an almost silent vigil kept in darkened labs. They peered into a microscopic world, hoping to see the shadow of a cosmic giant. Each cosmic ray track, a proton, a helium nucleus, an iron core stripped of its electrons, had to be analyzed and discarded. These were the background noise, the constant chatter of the universe. The monopole was the single pure note they strained to hear above the din. They found beautiful, intricate patterns of particle collisions. They saw the debris of atoms shattered by impacts, with energies far beyond anything humans could then create on Earth. They were mapping the raw, untamed nature of the cosmos, but the one track they sought remained stubbornly absent. The silence from the stratosphere was deafening. Every developed plate that came back clean, every year of scanning that yielded nothing, added weight to a terrifying possibility. Perhaps there was nothing there to find. Was the search flawed? Was the net too small, the exposure time too short? The sheer rarity of the monopole was a profound problem. If only a few were created in some distant ancient cataclysm, the chances of one happening to strike a dinner plate-sized detector dangling from a balloon over New Mexico were infinitesimally small. It was like trying to catch a single specific grain of sand dropped from orbit onto all the beaches of the world. The hunters refined their methods. They flew larger detector arrays for longer periods. They used new materials, plastics, that would record the passage of charged particles as microscopic tunnels etched into clarity by caustic chemicals. These new techniques allowed for larger surface areas and easier scanning, but the result was the same. The data was a book with millions of pages, and the one word they were looking for wasn't in it. They were reading the biography of the universe written in cosmic rays, and the main character seemed to be missing from the story. If nature would not deliver a monopole to their doorstep, then perhaps, just perhaps, they could force its hand. A new front in the war on ignorance was opening up on the ground. The age of the particle accelerator was dawning. These were the modern cathedrals of physics, great rings and tunnels of humming magnets designed to do one thing: take ordinary matter, protons and electrons, and accelerate them to fractions of the speed of light before smashing them together. Here, in these tightly controlled collisions, Einstein's famous equation E equals mc squared was not just a theory, it was an industrial process. Energy, pure and raw, could be concentrated into a microscopic fireball, and from that energy, new particles could be born. Particles heavier and more exotic than anything that makes up our everyday world could be forged in these crucibles of creation, if only for a fleeting instant. The logic was inescapable. If magnetic monopoles had mass, they could in principle be created from the energy of a collision. The recipe was simple in concept, but fiendishly difficult in practice. You would need to collide two known particles, say two protons, with enough energy to equal the mass of a new monopole-antimonopole pair. The intense electromagnetic chaos of the impact could theoretically tear a north pole away from a south pole, creating two free agents that would then fly apart into the detectors. The search shifted from the silent expanse of the upper atmosphere to the noisy, humming, radiation-filled halls of laboratories like Brookhaven on Long Island and CERN on the French-Swiss border. Here, physicists weren't just listening to the universe, they were shouting at it, trying to provoke it into revealing its secrets. The experimental setup was a testament to human ingenuity. A beam of protons accelerated to incredible energies would be slammed into a fixed target, a block of beryllium or tungsten. The resulting cataclysm would be a shower of shrapnel, a spray of hundreds or thousands of known particles, pions, kaons, neutrons, a whole zoo of ephemeral entities. Buried somewhere in this violent storm of debris, physicists hoped to find their prize. The challenge was now one of signal versus background. How do you spot the one strange particle you're looking for amongst a billion other distractions? Again, they relied on its predicted outrageous magnetic charge. A monopole produced in the collision would be grabbed by the accelerator's own powerful magnetic fields, the very fields used to guide the initial proton beam. Instead of flying straight into a detector, a north pole would be violently wrenched in one direction, while a south pole would be yanked in the opposite. Physicists could set up specialized traps detectors placed far away from the main spray of collision debris in places where no ordinary electrically charged particle should ever be able to reach. Finding a particle in one of these traps would be an unambiguous revolutionary discovery. The experiments ran the great machines powered up, consuming enough electricity to power small cities. Protons met their targets billions of times per second, and the traps remained empty. They increased the energy. The bevatron, the cosmotron, the proton synchrotron, each new machine pushed the frontier of energy higher, creating more violent and more energetic collisions. They were climbing a mountain of energy, hoping that the summit, the energy required to create a monopole, was just over the next ridge. But with every new, more powerful accelerator, the mountain simply seemed to grow taller. The silence from the accelerator halls began to echo the silence from the stratosphere. The lack of discovery was in itself a powerful piece of data. It told physicists that if monopoles existed, they had to be heavy, very heavy. Each failed experiment set a new lower limit on the monopole's possible mass. By the early 1970 seconds, it was clear that if Dirac's particle was real, it was a true heavyweight, far more massive than the proton, perhaps even heavier than entire atoms. It was too massive to be produced by the accelerators of the day, and seemingly too rare to be caught by the balloon experiments. The search began to feel like a paradox. The very theory that predicted the monopole placed no limit on its mass, leaving experimentalists with no signposts, no indication of how high they needed to climb. For a time, the hunt for the magnetic monopole receded from the frantic foreground of physics. It became a background hum, a persistent but seemingly unsolvable problem. The brightest minds in particle physics were preoccupied with a different, more immediate puzzle, bringing order to the burgeoning zoo of newly discovered subatomic particles. They were constructing what would become known as the Standard Model of Particle Physics, a magnificent theoretical edifice that described three of the four fundamental forces of nature: the strong nuclear force, the weak nuclear force, and Electromagnetism with breathtaking precision. It was a theory of division. It treated these forces as distinct entities, each with its own carrier particles and its own mathematical rules. It worked perfectly. But to some, this perfection felt incomplete, even unsatisfying. Why three forces? Why should the universe at its most fundamental level be so disunited? Physicists have always been driven by a deep-seated belief in simplicity, an aesthetic desire for unification. Just as Maxwell had unified electricity and magnetism into a single force a century earlier, a new generation of theorists dreamed of the next grand synthesis. They began to ask a daring question. What if the strong, weak, and electromagnetic forces are not truly separate? What if they are just different manifestations, different low-energy facets of a single, majestic underlying force that once governed the entire cosmos? This was the genesis of the grand, unified theories or guts. These theories were a monumental leap of imagination. They proposed that if you could turn up the energy of the universe, if you could recreate the conditions of the Big Bang, the distinctions between the forces would melt away. They predicted that at unimaginably high temperatures, trillions upon trillions of times hotter than the core of our sun, the strong, weak, and electromagnetic forces would merge their identities, becoming one and the same. In this primordial, superheated state, the universe would have been a simpler, more symmetric place. There was no difference between a quark and an electron. There was only one kind of particle and one kind of force. This state of perfect unity, however, could not last. As the infant universe expanded and cooled, this symmetry had to break. It was a process akin to a phase transition, like water freezing into ice. As the temperature of the universe dropped below a critical threshold, the single unified force froze out into the three distinct forces we see today. The strong force separated confining quarks inside protons and neutrons. The weak and electromagnetic forces then went their separate ways. The very structure of our physical reality, the rules that govern chemistry, life, and the stars, is a fossil of this ancient cooling. And it was here in the mathematics describing this cataclysmic universe-defining phase transition that something absolutely astonishing reappeared. The equations of the grand unified theories, developed for entirely different reasons and without any thought of Dirac's old puzzle, independently and unavoidably predicted the existence of magnetic monopoles. But these were not necessarily Dirac's monopoles. These were something new, something far grander and far more terrifying. The gut monopoles were not just particles, they were topological defects. They were flaws, wrinkles left over in the very fabric of space-time as it cooled and condensed into its modern form. Imagine the water freezing into ice again. If it freezes from many different points at once, the crystalline structures won't all align perfectly. Where these different domains of aligned crystals meet, you get defects, boundaries, and imperfections in the ice. In the same way as the universe froze and the unified force shattered, different regions of the cosmos might have settled into their new state with different orientations of the electromagnetic field. At the points where these different regions met, the equations demanded the formation of a stable, knot-like structure, a point-like defect where the magnetic field lines had nowhere to go. A magnetic monopole, this was a stunning convergence of ideas. A solution to the problem of charge quantization from the 1930 seconds had re-emerged unbidden from the most advanced theories of cosmic origins in the 1970 seconds. It was as if two separate teams of explorers starting on opposite sides of a continent had tunneled through a mountain and met in the middle. The discovery breathed new life into the entire field, but it also presented a staggering new challenge. According to the guts, the energy at which this symmetry breaking occurred was colossal. And because the mass of the monopoles created would be proportional to this energy, the gut monopole was predicted to be an absolute monster, not just heavier than a proton, but 10 million billion times heavier. The mass of a single GUT monopole would be comparable to that of an amoeba or a grain of dust, all compressed into a volume smaller than a proton. This incredible prediction changed everything. It explained at once why the particle accelerators had never found a monopole. Creating such a behemoth in a collision would require an accelerator the size of our solar system, a feat utterly beyond human capability for the foreseeable future, perhaps forever. The only accelerator powerful enough to forge a gut monopole was the Big Bang itself. Suddenly, the search was no longer just for a missing particle. It was a search for a cosmic fossil, a pristine relic from the first trillionth of a second of time. If a gut monopole could be found, it would be direct physical evidence of a state of matter and a unification of forces that we could never hope to recreate on Earth. It would be a message in a bottle from the moment of creation. The quest was now bifurcated, split into two parallel hunts. There was still the possibility of the light conventional Dirac monopole, a particle that might just be within reach of the next generation of accelerators. But now there was also the hunt for the super-heavy gut monopole, a creature that could only have been forged in the inferno of the birth of the universe. This second search would require a complete change of strategy. You couldn't make them. You couldn't hope to find them in the routine drizzle of today's cosmic rays. You had to look for the few ancient survivors that may still be drifting through the cosmos, ghostly leviathans coasting through the vast darkness, waiting to be found. The theoretical landscape had broadened, the stakes had been raised, and the hunt which had once seemed to be winding down in failure was now reborn, more intense and more profound than ever before. The hunt had grown quiet. Decades of theoretical prophecy, from Dirac's elegant quantum whisper to the thunderous proclamations of grand unified theories, had settled into a long, patient, and profoundly silent vigil. Across the planet, in laboratories shielded from the ceaseless chatter of cosmic rays, physicists had laid their traps. They were listening for the footstep of a ghost, the singular signature of a particle that ought to exist, that the deepest symmetries of our universe seemed to demand, yet which had never once shown its face. The search had become a testament to scientific faith, an enduring belief in a beauty and a symmetry that nature itself had stubbornly refused to confirm. We had built the most sensitive ears imaginable, yet all we heard was the familiar hum of the cosmos we already knew. An ocean of null, results of meticulously recorded nothingness, threatened to drown the entire enterprise in a sea of cold, hard, and deeply disappointing data. The grand quarry remained elusive, a phantom slipping through every net we could devise, leaving behind only the maddening echo of a perfect theory. In a basement laboratory at Stanford University, one such trap lay waiting. It was a device of sublime simplicity and almost unimaginable sensitivity, the brainchild of physicist Blas Cabrera. It was not a colossal accelerator smashing particles with brute force, nor a vast telescope staring into the abyss of space. Instead, it was a delicate, silent sentinel, a tiny, perfect loop of niobium wire, no bigger than your fingertip, suspended in the profound cold of liquid helium. At just a few degrees above absolute zero, this humble wire had become a superconductor, a place where electricity flows without any resistance, a perfect and frictionless river of charge. This state of quantum perfection transformed the simple loop into an extraordinary magnetic net. According to the laws of electromagnetism, any change in the magnetic field passing through the loop would induce a persistent, unwavering electrical current. The loop was in essence a flawless memory for magnetic events, a permanent record keeper designed to register the passage of our universe's most wanted fugitive. For months it had done its job with unwavering precision, which is to say, it had recorded absolutely nothing of interest. The current flowing through it remained stable, a flat, unwavering line on a chart recorder, disturbed only by the tiniest, most predictable thermal jitters. It was a monument to stability, a quiet vigil held in the heart of a world of chaotic noise. The entire apparatus was encased in layers of mu-metal shielding, a fortress against the Earth's own magnetic field and the stray electromagnetic whispers of a technological civilization. Cabrera's experiment was an island of pure, controlled quiet, designed to hear a single specific note above the background noise of reality. That note, the one he was listening for, was the unique calling card of the magnetic monopole. As this lone magnetic pole would pass through the superconducting ring, it was predicted to create a sudden, instantaneous and permanent jump in the current. A jump of a very specific size, a quantum leap dictated by the fundamental constants of nature. It would not fade, it would not waver. It would be a permanent change, a lasting scar on the otherwise perfect stillness of the system, the ghost's indelible fingerprint left behind in the cryostat. Then, on February 14th, 1982, the universe decided to send a Valentine. At 1:53 p.m. Pacific Standard Time, in the silent, cold heart of the apparatus, something extraordinary happened. The unwavering line on the chart recorder, the symbol of months of patient nothingness, leaped. It jumped upwards with a vertical, instantaneous precision that defied any mundane explanation. There was no gradual rise, no messy fluctuation. It was a perfect step function, as if a cosmic switch had been flipped. For a physicist, it was like hearing a single, impossibly pure musical note played in a soundproof room. Cabrera and his team, upon reviewing the data, must have felt a jolt of adrenaline mixed with profound disbelief. They checked everything. Could it have been a seismic tremor? The instruments were designed to be immune. A sudden change in the Earth's magnetic field. The multiple layers of shielding made that vanishingly improbable. A flaw in the electronics, a surge from the power grid, a simple mechanical failure. Every diagnostic, every calibration, every system check came back clean. The instrument was performing perfectly. It had simply seen something, and what it had seen was breathtaking. The jump in the current corresponded to a change in magnetic flux of exactly 8 quanta. Not 7.9, not 8.1, 8. Precisely the value, the specific integer multiple of the fundamental magnetic charge predicted by the most advanced theories for the passage of a single magnetic monopole. It was the signature, the perfect, clear, unambiguous smoking gun. The data wasn't just suggestive, it was shouting. It was a pristine event, a textbook example of what they had been searching for, appearing as if it had been lifted directly from a page in a theoretical physics journal and imprinted onto reality. For one crystalline moment, it seemed the long silence had been broken. The ghost had walked through the wall, and Blas Cabrera's delicate trap had not just caught its shadow, it had recorded its soul. The news, when it finally broke, did not ripple through the scientific community. It detonated. The publication of the Valentine's Day event sent a shockwave of euphoric excitement around the globe. It was the kind of discovery that changes everything. A potential crack in the foundations of the standard model of particle physics, offering the first glimpse of the grander unified structure that lay beyond. It was for a moment the dawn of a new era. In laboratories from Chicago to Geneva, from Italy to Japan, research groups scrambled with a frantic urgency. Plans for larger, more sensitive detectors were dusted off and fast-tracked. Funding proposals were written with a newfound confidence. The race was no longer to be the first to find a monopole, but to be the second, to provide the crucial confirmation that would elevate Cabrera's single, lonely data point from a tantalizing anomaly into a revolutionary discovery worthy of a Nobel Prize. The world's physicists were caught in a collective state of electrified anticipation, certain they were on the precipice of a paradigm shift. At Stanford, every conceivable mundane explanation was chased to ground. Cabrera and his team became the most meticulous detectives, interrogating their own experiment with a ruthless skepticism. They cooled and warmed the apparatus, testing for any unknown mechanical stress that could have mimicked the signal. They analyzed seismic data from the time of the event, finding nothing more than the faintest terrestrial hum. They even entertained the wilder possibilities. Could a stray cosmic ray, an exotic high-energy particle from deep space, have hit the apparatus in just the right way to create a false positive? The simulations and calculations showed that while not impossible, the probability was astronomically low. The energy deposition and the magnetic signature simply didn't match. An infamous story circulated about a graduate student who, as a prank, might have walked by with a powerful magnet hidden in their pocket. But this too was ruled out. The shielding was too robust, and the precise quantized nature of the signal was inconsistent with the messy, fluctuating field of a simple bar magnet. As they peeled back layer after layer of conventional physics, eliminating one possibility after another, the extraordinary conclusion became ever more difficult to escape. They had ruled out the mundane. They had eliminated the accidental. They had accounted for the improbable. What remained standing alone in the stark light of their analysis was the monopole, the beautiful, impossible, perfect candidate. For months, the world held its breath. Every day, physicists would check the preprint servers waiting for the bulletin from another lab. We saw it too. The community was poised, ready for the floodgates to open. Surely, if one had passed through Cabrera's tiny loop, then countless others must be streaming through the Earth at all times. The new, far larger detectors, with collecting areas hundreds or even thousands of times greater than the original Stanford experiment, were now online. They were listening with an even greater sensitivity, a planetary-scale network of traps laid for the cosmic wanderer. But the floodgates never opened. Days turned into weeks. Weeks bled into months, and then into years. The chart recorders in laboratories across the world traced out the same flat, unwavering lines that Cabrera's had before that fateful February afternoon. An unnerving, profound silence descended once more upon the search. The second event never came. Not at Stanford, where Cabrera built larger and more sophisticated detectors. Not in the Gran Sasso underground laboratory in Italy, where the massive macro experiment ran for over a decade. Not anywhere. The universe, having seemingly shown its hand for one brief, brilliant moment, had suddenly become shy. The single perfect note had faded, and the orchestra of the cosmos had returned to its familiar tune, leaving behind only a haunting memory of what could have been. The Valentine's Day monopole became one of physics' most celebrated and frustrating ghost stories. It was a discovery suspended in amber, a perfect data point that could neither be confirmed nor definitively refuted. It had all the hallmarks of a genuine discovery. It was clean, it matched theory with uncanny precision, and it had survived the most intense scientific scrutiny imaginable. Yet it failed the single most important test of all: repeatability. Science is built on a foundation of evidence that can be independently verified. A phenomenon that occurs only once under a single set of circumstances in a single laboratory cannot by definition become established scientific fact. It remains an outlier, an anomaly, a tantalizing what-if. The event which had once promised to begin a new chapter in physics now became its most famous footnote. The surge of experimental activity it had inspired was not in vain, however. While the new generation of detectors never found another monopole, they accomplished something else of immense scientific value. They began to place extraordinarily stringent limits on how many monopoles could possibly exist. With each passing year of silence, the net grew tighter. The data from these massive silent experiments told us that if magnetic monopoles are streaming through our galaxy, they must be incredibly, fantastically rare. Far rarer than even the most pessimistic models had predicted. The search that began with a bang of excitement had transformed into a slow, methodical process of elimination. We weren't finding where the monopoles were. We were discovering with ever-increasing certainty all the places they were not. The legacy of the Stanford event is therefore a complex and deeply paradoxical one. It represents both the pinnacle of hope and the depths of mystery in the quest for the monopole. It was a fleeting glimpse of a promised land that we have never been able to find again. Did Blas Cabrera and his team witness the genuine passage of a relic from the birth of the universe, a particle carrying a primordial magnetic charge? Was it a once-in-a-civilization event, the capture of an entity so cosmically scarce that we may never see another? Or was it in the end a cosmic coincidence of unimaginable improbability? A subtle conspiracy of noise and instrumentation that for one brief moment perfectly mimicked the signature of our deepest theories. We are left with a ghost in the machine, a perfect signal without a source, a question mark stamped into the history of science. The single unrepeated event forced us to confront a far more profound and unsettling question. If the grand unified theories are correct, if monopoles were forged in the inferno of the Big Bang, they should have been created in colossal numbers. The universe should be awash with them. Our detectors should be screaming with signals, not sitting in stony silence. The Valentine's Day event, in its splendid isolation, only deepens this paradox. It suggests they might exist, but their shocking scarcity points to a fundamental flaw in our understanding of the universe's first moments. Why is the cosmos so empty of the very things it should have made in abundance? The deafening silence that followed that one tantalizing shout from the void forced us to look back to the very first fraction of a second of creation, itself searching for an answer to one of physics's greatest vanishing acts. Where did all the monopoles go? That single fleeting signal in a Stanford basement had electrified the world of physics. It was a whisper from the wilderness, a ghost in the machine that hinted for one tantalizing moment that Paul Dirac's beautiful abstraction was real. But as physicists around the globe scrambled to build their own superconducting loops desperate to replicate Blas Cabrera's discovery, the theorists were wrestling with a paradox, a problem of such cosmic proportion that it threatened to shatter their most elegant vision of the universe. It became known with quiet dread as the monopole problem. The issue wasn't that monopoles were hard to find. The issue was that, according to our best theories, they should have been impossible to miss. You see, the grand unified theories, or GUTS, which so beautifully braided together the strong, weak and electromagnetic forces into a single primordial entity, came with a prophecy. They predicted that as the universe cooled from the inferno of the Big Bang, it would have undergone a series of phase transitions, cosmic moments of profound change. Think of water freezing into ice. As the liquid cools, crystals form, but they don't all form perfectly aligned. Where different crystalline domains meet defects, appear cracks and imperfections in the structure of the ice. The early universe in its rapid, violent cooling would have done something similar. As that single unified force fractured and froze into the distinct forces we see today, the very fabric of space-time would have developed defects at the boundaries of these cosmic domains. And the inevitable, unavoidable point-like defects predicted by the theory were magnetic monopoles. They weren't just a possibility, they were a cosmological necessity. These gut monopoles would have been primordial relics forged in the first nanofraction of a second. They would be incredibly, almost unbelievably massive, perhaps 10 quadrillion times heavier than a proton, packing the mass of an amoeba into a single fundamental particle. And according to the simplest models, they should have been produced in staggering numbers. As the universe expanded, they would have been carried along for the ride, a kind of primordial confetti scattered throughout the cosmos. Herein lay the terrifying contradiction. If the guts were right, these monopoles should be everywhere. Their immense mass meant they would exert a powerful gravitational pull. They would have clumped together, seeding the formation of galaxies and clusters. In fact, the calculations were stark and unforgiving. There should be so many monopoles that their combined gravity would vastly outweigh all the stars, gas and dust we can see. The universe should be so dense with them that its expansion would have long ago halted, reversed and collapsed back on itself in a fiery big crunch. Our very existence in a sprawling, expanding cosmos was a direct refutation of this prediction. We looked out into the night sky and saw not a universe groaning under the weight of magnetic relics, but one expanding, accelerating, and seemingly devoid of them. It was a crisis of cosmic accounting. Where did all the monopoles go? Did this paradox kill the beautiful idea of grand unification? For a time, it seemed physics had painted itself into a corner, creating a magnificent theoretical edifice that was completely at odds with reality. The search for a single monopole in a lab seemed almost quaint compared to the search for the missing mass of the entire universe. The solution, when it arrived, was as audacious as the problem it solved. It came not from a particle physicist trying to tweak the properties of the monopole, but from a young cosmologist named Alan Guth, who was grappling with entirely different cosmic puzzles. He wasn't trying to hide the monopoles, he was trying to understand why the universe was so big, so flat, and so remarkably uniform from one horizon to the other. His answer, proposed in 1981, was a radical new chapter in the story of creation cosmic inflation. The idea was breathtaking in its scope. Guth proposed that for a fleeting, almost incomprehensible moment, from about 10 to the -36 to 10 to the -32 seconds after the Big Bang, the universe underwent a period of exponential, hyper-accelerated expansion. This wasn't just the normal stately expansion we see today. This was a violent, explosive stretching of space-time itself, driven by the energy of a false vacuum state. In this sliver of a second, a region of space smaller than a proton was stretched to a size larger than our entire observable universe today. It was as if the cosmic floodgates had been thrown open, unleashing a tidal wave of space-time that smoothed out any initial wrinkles or curvatures. This inflationary epoch elegantly solved the problems Guth was worried about. It explained why distant regions of the cosmos, which should never have been in contact, share the same temperature they were once intimately connected before inflation ripped them apart at superluminal speeds. It explained why the geometry of our universe appears perfectly flat, just as the surface of a tiny balloon appears flat if you inflate it to the size of the Earth. And then, almost as a side effect, a bonus gift of staggering importance, it solved the monopole problem. The monopoles, according to the Guts, would have been produced just before this inflationary burst. For a brief instant, the newborn universe was indeed a thick hot soup teeming with them. But then inflation began. Imagine a single drop of ink suspended in a tiny sphere of water. Now, in an instant, that sphere of water is expanded to the size of a planetary ocean. The drop of ink, the monopoles, is still there, but it has been diluted to an absurd degree. Its constituent molecules are now separated by light years. To find a single one in that vast ocean would be a near impossible task. This is what inflation did to the primordial monopoles. It took the impossibly dense swarm predicted by the Guts and spread them so thinly across the cosmos that the probability of one of them residing within our observable universe could be vanishingly small. Perhaps there is only one Gut monopole in our entire galactic neighborhood. Perhaps there are none at all within the bubble of space-time we can ever hope to see. Inflation didn't erase the monopoles, it hid them. It preserved the elegant predictions of grand unification, while simultaneously explaining their phantom-like absence. It was a theoretical masterstroke, transforming the monopole from a cosmic blunder into an ultra-rare, almost mythical messenger from a time before time as we know it. The search was no longer for an abundant particle, but for a lone survivor, a castaway from the pre-inflationary era. The challenge for experimentalists was now redefined. Cabrera's single loop, elegant as it was like a fisherman's net in an ocean the size of a galaxy. To have any real hope of catching such a rare creature, the hunt had to scale up dramatically. The new generation of detectors would not be built on laboratory benches, but carved out of mountains and assembled in colossal underground caverns. The quest drove physicists deep into the Earth, seeking refuge from the cosmic static. Our planet is constantly bombarded by a rain of high-energy particles from space, cosmic rays, which create a storm of secondary particles in the atmosphere. For a sensitive detector looking for a single, unique event, this background noise is a blinding fog. The only way to escape it is to use the Earth itself as a shield. And so, in the late 1982, an international collaboration began constructing a fortress of science in the heart of Italy's Gran Sasso mountain range. Beneath 1,400 meters of solid rock, in a series of immense halls carved from the mountain, they built the Monopole Astrophysics and Cosmic Ray Observatory, or MACRO. It was a behemoth, vastly larger than any monopole detector that had come before it. MACRO was a multi-story, multi-layered giant designed to be a near-perfect monopole trap. It wasn't just one type of detector, but three working in concert to provide an unambiguous signature. The outer layers were made of liquid scintillators, vats of special fluid that would emit a flash of light when a charged particle passed through. A slow-moving massive monopole was predicted to produce a long, sustained trail of light, radically different from the fleeting spark of a typical cosmic ray muon. Interspersed with these were layers of streamer tubes, gas-filled detectors that would map the particle's trajectory with precision, creating a digital breadcrumb trail of its path. Finally, sheets of track-etched plastic would act as a kind of fossil record. A highly ionizing particle like a monopole would scar the plastic, leaving a microscopic tunnel of damage that could be revealed later with chemical etching. Any candidate signal would have to satisfy all three systems. It would need to leave a long flash of light, a straight track, and a physical scar. This triple redundancy was designed to eliminate any possibility of a false positive, any chance of being fooled by a strange coincidence of background noise. For more than a decade, MACRO stood its silent, subterranean vigil. It listened to the cosmos, shielded by the mountain's stony silence. Its computers tirelessly sifted through the data from hundreds of millions of events, Countless muons born in the atmosphere above rained down through the rock, streaking through the detectors and providing constant calibration. Neutrinos from the sun and distant supernovae passed through like ghosts, barely interacting at all. The team waited. And waited. They were searching for a single anomalous track, a particle moving at a fraction of the speed of light, lit up like a Christmas tree from its immense magnetic charge, marching inexorably through their trap. It would be the particle physics discovery of the century. But the signal never came. Years turned into a decade. The seasons changed on the mountain above, but deep in the laboratory the result remained the same, a profound and echoing silence. When the experiment was finally decommissioned in the year 2000, its conclusion was one of the most powerful negative results in the history of physics. Macro hadn't found a monopole, but it had drawn a sharp, definitive line in the sand. It had placed the most stringent upper limit yet on the flux of these cosmic relics, telling us that if they are streaming through our galaxy, they are rarer than even the most pessimistic models had suggested. The great subterranean hunt had come up empty, deepening the enigma. If we couldn't find a primordial monopole that had been wandering the cosmos for 13 billion years, perhaps there was another way. Perhaps we could make our own. This impulse gave rise to the second great strategy of the modern search, a brute force approach born not of patient listening, but of spectacular controlled violence. The goal shifted from cosmic archaeology to particle alchemy to recreate the unimaginable energies of the Big Bang right here on Earth. To do that, we would need to build the most powerful machine in human history. On the border of France and Switzerland, buried 100 meters underground, lies a 27-kilometer ring of superconducting magnets and accelerating cavities, the Large Hadron Collider. The LHC is a modern-day cathedral, a temple dedicated to the fundamental forces of nature. It is a time machine designed to wind the cosmic clock back to the first trillionth of a second after the moment of creation. Inside its twin beam pipes, bunches of protons are accelerated to 99.9999991% of the speed of light, whipping around the ring over 1,1,0,0,0 times a second. At 4 specific points, these beams are steered into a head-on collision. In these points of impact inside detectors the size of apartment buildings, Einstein's famous equation E equals mc squared is made manifest. The raw kinetic energy of the protons is converted into a shower of new exotic particles, many of which haven't existed freely in the universe since its birth. It was here in this man-made inferno that the Higgs boson was finally cornered in 2012. And it is here that physicists now hunt for the magnetic monopole. The strategy is different from macros. At the LHC, we aren't looking for a slow, heavy gut monopole from the dawn of time. The energy of the collider, while immense, is still many orders of magnitude too low to create a particle as massive as a gut monopole. Instead, the search is for lighter hypothetical monopoles, perhaps born from different physics like certain extensions of the Standard Model or string theory. Even if a lighter monopole could be produced, it would manifest in a truly spectacular fashion. According to theory, a collision could produce a monopole-anti-monopole pair. Because of their enormous magnetic charge, they would not behave like ordinary particles. They would rip through the detector with ferocious energy, aggressively ionizing the material they pass through. Their signature would be unmistakable, a track of light and energy deposition thousands of times more intense than that of any normal particle. It would be like a celestial blowtorch searing a path through the detector's silicon heart. The two main experiments, ATLAS and CMS, two of the most complex scientific instruments ever built, are designed to catch just such a signature. Their powerful magnets would bend the paths of these particles, and their calorimeters would measure the incredible dump of energy they leave behind. For years now, since the LHC began its record-breaking runs, specialized teams have scoured the torrential flood of data. Trillions upon trillions of collisions have been recorded, each one a tiny reenactment of the Big Bang. Sophisticated algorithms, a form of artificial intelligence, sift through petabytes of information, hunting for that one anomalous high-energy track. It is a search for a needle of impossible brightness in a haystack of cosmic proportions. And yet, once again, the universe remains silent. Collision after collision, run after run, the result has been the same. Quarks, gluons, bosons, and all the familiar particles of our world have appeared in abundance. But of the magnetic monopole there has been no trace. Not a single event in the LHC's vast library of cosmic collisions has borne the telltale signature of Dirac's phantom. We find ourselves in a strange and beautiful scientific predicament. We stand between the towering theoretical edifice of grand unification, which screams that monopoles must exist, and the profound, deafening silence from our grandest experiments. Inflation provides a graceful, compelling explanation for why the ancient ones are so hard to find. But the null results from the LHC, our own particle forge, add another layer of mystery. This persistent absence is not a failure, it is a message. The universe is telling us something deep, something subtle about its fundamental nature. The lack of evidence is itself a powerful piece of evidence. It forces us to ask harder questions. Is our understanding of the early universe of unification incomplete? Are we looking for the right kind of monopole? Could they exist not as physical particles we can hold or create, but in some other, more ethereal form woven into a mathematical fabric of reality itself? The chase is far from over. It has simply become more refined, more cunning. The silence has pushed us away from the grand, simple picture of the 1,980 seconds and toward a landscape of new, more exotic possibilities, where the quarry we hunt may be far stranger than we ever imagined. For decades, the search had stretched across the cosmos, a grand and noble failure. We built colossal nets of superconducting wire hoping to ensnare a ghost. We repurposed particle accelerators, those cathedrals of modern physics, to try and forge one from pure energy. We pointed our cosmic ray detectors to the heavens, listening for the telltale shout of a primordial titan streaking through our atmosphere. Yet after all the effort, all the ingenuity, all the years spent watching and waiting, the universe had offered only a profound and deafening silence. The great monopole hunt, born from Dirac's elegant mathematics and fueled by the explosive predictions of the Big Bang, seemed to have reached a dead end. The silence felt like an answer, a verdict declaring that this beautiful, symmetrical idea was perhaps just that, an idea. But science in its relentless curiosity is never truly defeated by a lack of evidence. When one door closes, when one avenue of inquiry grows cold, it develops a remarkable habit of finding a new way in, often through a side entrance we never even knew existed. The grand cosmic search had stalled, so physics did something unexpected. It looked down. It turned its gaze away from the unfathomable scales of galactic clusters and nascent stars, and focused instead on something you could hold in the palm of your hand. The next great chapter in the story of the magnetic monopole would not be written in the language of cosmology, but in the strange crystalline whispers of solid-state physics. Here, in the quiet, ordered world of condensed matter within materials cooled to within a breath of absolute zero, we were about to find the very thing we had been searching for. Not as a fundamental particle, a relic of creation, but as something far stranger, and in some ways far more instructive, a ghost in the machine, a perfect imposter born from collective desperation. The key to this astonishing discovery lies within a peculiar class of materials known as spin ices. Imagine a crystal, a perfectly repeating lattice of atoms. One of the most common is a substance called dysprosium titanate. At first glance, it is unremarkable. Yet, as we zoom in deep into its atomic architecture, we find a structure of exquisite complexity. The magnetic atoms, the dysprosium ions, are not arranged in a simple grid, but in a network of interconnected pyramids, tetrahedra, sharing their vertices. Each of these atoms possesses a powerful magnetic moment, a spin which acts like a tiny subatomic compass needle. And like any compass needle, it wants to align itself. But here, within this crystalline pyramid scheme, a profound dilemma arises. The natural interactions between the atoms dictate that on each tetrahedron, two of the spins must point inwards towards the center of the pyramid, and two must point outwards. It's a rule born from the fundamental drive to find the lowest possible energy state, a state of magnetic contentment. This arrangement, this two-in, two-out configuration, is eerily familiar to physicists. It is the exact same geometric rule that governs the position of hydrogen atoms in ordinary water ice, a deep and unexpected connection between the behavior of magnetism and the structure of frozen water. Under normal circumstances, at high temperatures, the atoms have enough thermal energy to jiggle and flip their spins randomly. The system is a chaotic mess of magnetic arrows constantly reconfiguring themselves. But as you cool the material down, stripping away that thermal energy, the spins begin to settle. They try to obey the two-in, two-out rule everywhere at once. And it is here that they run into a problem, a state known as geometric frustration. In a simple magnet, every spin can align perfectly with its neighbours, all pointing north, creating a state of perfect boring order. But in the tetrahedral lattice of spin ice, it's impossible. Satisfying the rule on one tetrahedron can create a conflict for the one right next to it. The system as a whole can never find a single perfect lowest energy ground state. It is trapped in a state of perpetual compromise, a frozen dance of magnetic indecision. There are countless ways to arrange the spins to satisfy the two-in, two-out rule, all with the exact same low energy. The crystal settles into one of these states, a snapshot of frozen, frustrated order. It is within this very frustration, this inability to find perfect peace, that the miracle occurs. For this strange, cold and indecisive crystal was about to become the world's first monopole nursery. Imagine we are now deep inside this silent, frozen lattice. Every tetrahedron is content for the moment, with its two spins pointing in and two pointing out. The magnetic field lines flow through the crystal like a closed continuous fluid with no beginning and no end. But now let's add a tiny bit of energy, just enough to persuade a single magnetic atom to flip its orientation. One arrow that was pointing inwards now points outwards. In that one microscopic instant, the delicate balance is shattered. We have broken the rule. On the tetrahedron where the flip occurred, we now have a 3-in, 1-out configuration. This creates a powerful convergence of magnetic field lines, a point from which magnetic flux now radiates outwards. It is, for all intents and purposes, a source. It is an effective North Pole, but the consequences of that single flip do not end there. Remember that spin was part of two tetrahedra. By flipping from in to out on the first pyramid, it necessarily flipped from out to in on its neighbour. So at the centre of that adjacent tetrahedron, we have simultaneously created the opposite defect, a 1-in, 3-out configuration. This becomes a point where magnetic field lines converge, a sink for magnetic flux. It is an effective South Pole. What we have just witnessed is the birth of a monopole-antimonopole pair. They are not fundamental particles chiseled from the fabric of space-time in the Big Bang. They are what physicists call quasi-particles, not real particles in the traditional sense, but emergent phenomena, collective behaviors of the underlying atoms that behave with a startlingly independent identity. They are disturbances in the magnetic order that take on a life of their own. And here is the truly incredible part. Once created, these two defects are no longer tied to each other. With another small injection of energy, a neighbouring spin can be encouraged to flip, and then another and another. As this cascade of flips propagates through the crystal, the North Pole defect effectively moves one way and the South Pole defect moves the other. They are free. They can wander through the crystalline labyrinth completely independent of one another. We have created inside a solid material a population of mobile, stable north and south magnetic charges. We have, in essence, boiled magnetism, liberating individual poles from their partners in a sea of frustrated spins. We had searched the heavens for a single cosmic North Pole, and instead we found an entire civilization of them, living and moving within the frozen heart of a crystal. The importance of this discovery cannot be overstated. It was more than just a clever trick of condensed matter physics. It was a paradigm shift in the entire quest. For the first time, we had a controllable laboratory to study the behavior of these elusive entities. The theoretical playground of Dirac had become a tangible reality, a world we could probe and manipulate. We could watch as these quasi-particle monopoles drifted through the lattice, repelling their own kind and attracting their opposites precisely as theory predicted. Scientists could apply an external magnetic field and literally watch these magnetic charges flow, creating a current. Not a current of electrons, which is electricity, but a current of magnetic poles. They had discovered magnetricity. This wasn't just an analogy, it was a true magnetic analogue to an electric circuit governed by a magnetic version of Ohm's law. We could measure their charge, a direct confirmation of Dirac's quantization condition now realized in an emergent system. We could study their dynamics, their effective mass, how they scatter and interact. All the questions we desperately wanted to ask a fundamental monopole we could now ask of its perfect crystalline doppelganger. These synthetic monopoles, these ghosts born of frustration, have become one of the most powerful tools we have. They allow us to refine our understanding of how magnetic charges should behave, sharpening the very image of what we are looking for out there in the wider cosmos. They prove that the concept of a magnetic monopole is not just a mathematical fantasy. Nature knows how to make them. It has shown us the recipe, and this revelation has breathed new life into the original cosmic search. The discovery of synthetic monopoles didn't end the hunt for the fundamental particle. It reinvigorated it with a profound sense of possibility. If nature can manifest these properties in the collective behavior of a crystal, it reinforces the sheer elegance and likelihood of the idea at a fundamental level. The search today continues, but it is a search transformed smarter, deeper, and more sensitive than ever before. The brute force induction coils of the past have evolved into instruments of breathtaking precision. We are no longer just casting a wide net. We are designing cosmic fishing lines with hooks tailored to a very specific kind of prey. At the South Pole, buried a mile deep in the Antarctic ice cap, is the IceCube Neutrino Observatory. Its primary mission is to detect ethereal neutrinos, but its vast array of light sensors, a cubic kilometer of instrumented ice, also makes it one of the world's most potent monopole detectors. A primordial monopole, a true gut-scale titan, would be incredibly massive and moving at nearly the speed of light. If one were to tear through the pristine ice, it would produce an unbelievable cascade of Cherenkov radiation, a cone of blue light that would be catastrophically bright, far brighter than any other known particle event. It would be a signal so outrageously luminous, so unambiguously clear, that it would light up the detector like a cosmic flashbulb. So far, the ice has remained dark to such an event, but every second the watch continues. Elsewhere, the legacy of the superconducting loop continues in the form of SQUIDs, superconducting quantum interference devices. These are the most sensitive magnetometers ever created by humanity, capable of detecting changes in a magnetic field millions of times weaker than the Earth's. Modern experiments deploy arrays of these SQUIDs, creating a silent, vigilant perimeter, waiting for the tiny telltale magnetic signature of a single pole passing through. They are listening posts for the universe's oldest whispers, engineered with a quiet patience that borders on the sublime. The sensitivity is now so extreme that we are no longer just looking for the colossally massive monopoles predicted by the simplest grand unified theories. Those original theories, as we've seen, led to the monopole problem. They predicted far too many of these relics. The theory of cosmic inflation, our best model for the universe's first fleeting moments, provided a tidy solution by suggesting the universe expanded so rapidly that it diluted the density of monopoles to almost nothing, making them impossibly rare. This could explain the silence from our detectors. But what if the original predictions were not just overzealous but incomplete? Modern theoretical physics, including refinements from string theory and other exotic models, has opened the door to new possibilities. Perhaps monopoles are not so massive after all. Perhaps they exist at an intermediate mass scale too heavy to be created in our particle accelerators, but far lighter than the gut-scale behemoths. Such monopoles would be more plentiful, but their interactions with our detectors would be far more subtle, requiring the next generation of sensitivity to even notice their passage. Our theories now guide a more nuanced search, providing a wider spectrum of potential targets to hunt. The search has also expanded beyond our planet's immediate vicinity, turning the machinery of the heavens itself into a grand detector. We are now hunting for the monopole's astrophysical fingerprints, the subtle ways their existence might sculpt the cosmos on the grandest scales. Galactic magnetic fields, for instance, are a puzzle. We see them threaded through entire galaxies, vast, stable structures that help shepherd the birth of stars. But they shouldn't be so stable. How are they generated and sustained over billions of years? This is the dynamo problem, and it's one of astrophysics' great unsolved mysteries. The existence of even a tiny population of free-roaming magnetic monopoles could completely change the equation. Like rogue agents, they would be accelerated by these galactic fields, draining their energy, causing them to decay far faster than our observations permit. The fact that we see strong, stable magnetic fields across the universe places an incredibly strict upper limit on how many monopoles can be out there. The stability of the galaxy you inhabit becomes a piece of evidence in the case against the monopole. In a very real sense, every telescope that maps these fields is participating in the search. Other theories propose even more exotic roles. Could magnetic monopoles, with their predicted massive nature and weak interactions, actually be a component of the enigmatic dark matter that holds galaxies together? Could the annihilation of monopole-antimonopole pairs in the galactic halo produce gamma rays or other particles that our space telescopes might one day detect? We find ourselves then in a remarkable and thrilling moment in this centuries-long quest. The search is now advancing on two parallel fronts, each one informing and inspiring the other. In one world, we have the tangible reality of the spin ice crystal, a microcosm where we can create, control, and study magnetic monopoles at will. It is a perfect theoretical laboratory made real, a place to learn the language of magnetic charge, to understand its grammar and its syntax. In the other world, we have the ongoing cosmic vigil. It is a search defined by heroic engineering, by profound patience, and by a refusal to accept silence as the final answer. We are scanning the heavens and the earth from the frozen depths of our planet to the magnetic skeletons of distant galaxies for a single authentic voice from the dawn of time. One search gives us certainty about the concept, the other grasps for the reality of the original particle. Together they represent the pinnacle of scientific inquiry, the interplay between controlled experiment and bold exploration. We have found the ghost in the machine, and it has taught us how to better hunt the giant in the cosmos. The question is no longer simply do they exist, but has become a more refined, more hopeful query. Where have they been hiding? And so, after a century of relentless searching, we find ourselves here, standing before a profound and unnerving silence. The cosmos has not yet yielded its most elusive phantom. Through the deepest tunnels carved into mountains, beneath the crushing ice of the poles, and within the incandescent hearts of manufactured stars, we have listened. We have built cathedrals of science to capture a single, solitary note, a whisper of magnetic charge, isolated and pure. Yet the symphony of existence plays on without it. The ghost in the machine of electromagnetism, the particle whose existence would make our equations sing with perfect symmetry, remains a ghost. For all our ingenuity, for all our unwavering conviction, the fundamental magnetic monopole has not answered our call. The throne sits empty. But to mistake this silence for failure is to misunderstand the very soul of discovery. It is to miss the colossal, universe-altering story that this apparent emptiness has told us. The hunt for this one missing piece has, against all expectation, given us one of the most complete pictures we have ever had of the whole. It is a journey that has forced us to confront the birth of time itself, to rewrite the opening chapter of the cosmic story, and to reshape our understanding of what it means for a theory to be not just correct, but beautiful. Let us rewind the clock not to the beginning of the universe, but to the beginning of the idea. Travel back with us to a time before we could even conceive of smashing atoms together, a time when the deepest truths were plumbed not by colossal machines, but by the sheer, audacious power of a human mind, armed with nothing more than chalk and a blackboard. There, in 1931, a young Paul Dirac performed an act of intellectual alchemy. He looked at the elegant, near-perfect equations of James Clerk Maxwell, the four pillars that govern all of light, electricity, and magnetism. He saw a universe of breathtaking harmony, but with one jarring asymmetry. Electric charges, the familiar positive and negative electrons and protons, existed in glorious isolation. Yet, their magnetic counterparts, the North and South Poles, were forever bound together, condemned to an inseparable duality. Dirac simply asked, what if they weren't? What if nature at its most fundamental level did not play favorites? With that simple, profound question, he scribbled a new term into the universal blueprint. He posited the existence of a magnetic monopole. It was not a prediction born of experimental necessity. No observation at the time demanded it. It was instead a prediction born of a physicist's deepest instinct, the belief that the fundamental laws of nature must be elegant, symmetrical, and whole. The consequences of his idea were staggering. He demonstrated that if even a single magnetic monopole existed anywhere in the cosmos, it would elegantly and automatically explain one of nature's deepest and most baffling mysteries, the quantization of electric charge. The fact that every electron carries the exact same charge, that every proton carries the exact same but opposite charge, would no longer be a brute, unexplained fact. It would be a necessary consequence of a deeper magnetic symmetry. The monopole became a theoretical anchor, a keystone that, if it could be found, would lock the entire arch of quantum electrodynamics into a structure of sublime and unshakable logic. For decades, however, it remained little more than a theorist's dream, a beautiful piece of mathematics lingering on the fringes of physics, waiting for a connection to the real world. It was a compelling ghost story, but one without any physical evidence to substantiate it. That all changed in the 1,970 seconds, when our ambition grew from understanding individual forces to uniting them. Physicists, emboldened by their success in unifying electricity, magnetism, and the weak nuclear force, set their sights on an even grander prize, a grand unified theory, or GUT. They sought a single monolithic mathematical framework that would describe the electroweak force and the strong nuclear force, which binds atomic nuclei together as different facets of one primordial superforce. These theories were attempts to read the mind of God, to understand the physics that reigned in the first unimaginably energetic moments after the Big Bang. And as theorists built these magnificent theoretical edifices, a shocking and unavoidable prediction emerged from the mathematics. They didn't just allow for magnetic monopoles, they demanded them. The monopole was no longer an optional aesthetic flourish. According to these powerful new theories, monopoles were not rare. They should have been forged in colossal numbers during the fiery crucible of the universe's birth, as the primordial superforce shattered into the distinct forces we know today. They were to be cosmic fossils, super-heavy, stable relics of that initial unified state. The ghost, it seemed, was about to become terrifyingly real. Suddenly the search was on. The quiet academic curiosity transformed into a full-blown experimental gold rush. The predicted properties of these gut monopoles gave searchers a clear target. They would be astonishingly massive, thousands of trillions of times heavier than a proton carrying an immense magnetic charge. They would be the ultimate cosmic bullets moving through matter and leaving behind unmistakable trails of ionization. And so we began to build our nets. We repurposed detectors designed to catch cosmic rays, hoping to see the unique uniform energy signature of a monopole ploughing through. We laid out vast arrays of superconducting loops instruments of such exquisite sensitivity that the passage of a single monopole would induce a permanent telltale jump in the electrical current, a signature that could not be faked. Geologists began to analyze ancient rocks from the Earth's crust, and even lunar samples brought back by the Apollo missions, hoping to find a monopole that had been captured and trapped over billions of years. We scoured the heavens and the Earth. We went deep underground, using the planet itself as a shield to filter out the confusing noise of lesser particles, creating a pristine silence in which to listen for the monopole's magnetic shout. For a time, the excitement was palpable. The community held its collective breath, believing that the discovery was just around the corner. And then, on a fateful Valentine's Day in 1982, it seemed the moment had arrived. In a small shielded lab at Stanford University, physicist Blas Cabrera was monitoring just such a superconducting loop. After months of painstaking silent observation, the instruments jumped. The data showed a perfect quantized step in the magnetic flux, the exact unambiguous signature that a monopole had at long last passed through the detector. The news spread like wildfire. For a brief electrifying moment, it seemed the century-long quest was over. The ghost had been caught. But the celebration was short-lived. The signal never repeated. Despite building larger, more sensitive detectors, and despite decades of further searching by Cabrera and teams around the world, another such event has never been seen. The Valentine's Day monopole, as it came to be known, is now regarded as an instrumental glitch, a cruel fluke, a single anomalous blip in an otherwise unbroken history of silence. It was a tantalizing glimpse of a world that might have been a ghost that appeared for an instant, only to vanish forever. leaving behind more questions than answers. The continued silence from our experiments began to pose a terrifying problem, one far greater than just a missing particle. The grand unified theories which so beautifully promised to unite the forces of nature had a dark side. Their prediction of a massive outpouring of monopoles in the early universe led to a cosmological catastrophe. If the theories were correct as they stood, the universe should be filled with these super-heavy particles. Their combined mass would be so immense that their gravitational pull would have long ago halted the expansion of the cosmos and caused it to collapse back in on itself in a big crunch. Our universe would have been stillborn, crushed by the weight of its own magnetic ghosts. Yet here we are. We exist in a vast, ancient and expanding universe. This glaring contradiction between a beautiful theory and the stark reality of our existence became known as the monopole problem. It was a crisis of the highest order. It suggested that either our grandest theories of unification were fundamentally wrong, or our understanding of the Big Bang itself was desperately incomplete. The search for the monopole had backed us into a corner, forcing us to choose between two of the central pillars of modern physics, and it was here, in the depths of this intellectual crisis, that the true legacy of the monopole search was forged. In an effort to solve the monopole problem, to explain why the universe wasn't drowning in these particles, a young physicist named Alan Guth proposed a radical, audacious addition to the story of creation. He suggested that in the very first fraction of a second of its existence, the universe underwent a period of mind-bogglingly rapid expansion, a hyper-acceleration called cosmic inflation. In a fleeting moment, a patch of space far smaller than a proton swelled to a size larger than the observable universe today. This incredible stretching of the fabric of space-time would have been so extreme and so violent that it would have taken the dense swarm of monopoles forged in the initial Big Bang and diluted them to near nothingness. It would be like taking a single drop of ink in a glass of water and then expanding that glass to the size of Earth's oceans. The ink is still there, but the chance of finding a single molecule of it in any given sample becomes vanishingly small. Inflation explained perfectly why our universe is so large, so smooth, and so empty of magnetic monopoles. The theory was invented to solve the monopole problem. Think about the profound weight of that revelation. The monopole, a particle we have never ever seen, created a paradox so deep that the best solution was to completely revolutionize our model of the Big Bang. The search for this one invisible entity gifted us the theory of cosmic inflation, which has since become the bedrock of modern cosmology. It is a theory whose predictions about the large-scale structure of the cosmos and the subtle temperature fluctuations in the cosmic microwave background radiation have been verified with stunning precision. We did not find the object of our quest, but the quest itself led us to an even greater treasure. The map we drew to find a single mythical island revealed to us the true shape of the entire world. The ghost story, it turns out, was not about the ghost itself. It was about the house it was said to haunt the entire cosmos. This is the paradoxical triumph of the monopole. Its most significant contribution to physics to date has been its spectacular absence. The legacy does not end there. The relentless drive to find this single particle has pushed our technology to its absolute limits and beyond. The squids, those superconducting quantum interference devices built to detect a monopole's passage, are now among the most sensitive magnetic field detectors on Earth. They are used in medicine to map the faint magnetic fields of the human brain, and in materials science to probe the quantum behavior of novel substances. The massive, deeply buried detectors like IceCube in Antarctica while listening for monopoles have opened up a brand new window onto the cosmos, the field of neutrino astronomy, capturing ghost-like particles from distant, violent cosmic events. The search has been a crucible for innovation, forcing us to build ever more sophisticated eyes and ears, tools which we now turn to other cosmic mysteries. Even in the realm of pure theory, the monopole continues to inspire. The mathematics describing it has found surprising applications in understanding the strange quantum entanglements of particles and the very nature of space-time geometry. And in a tantalizing twist, physicists have discovered that monopole-like entities times exist not as fundamental particles roaming the cosmos, but as emergent quasi-particles within exotic crystalline materials known as spin ices. Inside these strange materials, the collective behavior of countless atoms conspires to create disturbances that behave exactly like a North Pole untethered from a South. Nature, it seems, knows how to create monopoles in a lab, even if it chose not to scatter them across the heavens. So where does this leave us? We are the inheritors of a century-long odyssey, a multi-generational quest for a particle born from a desire for mathematical beauty. We have followed its theoretical thread from the quiet contemplation of quantum mechanics through the fiery genesis of the Big Bang and into the heart of our grandest unified theories. We have chased its shadow with detectors of breathtaking scale and sensitivity, and in the end we stand with open but empty hands. Yet our gaze is not cast down in disappointment, but lifted to the cosmos with a newfound and far deeper understanding. We have learned that the universe is grander, stranger, and had a far more violent and dramatic beginning than we ever imagined. We have learned that even a wrong theory can be spectacularly fruitful, pointing the way toward a deeper truth. The monopole problem forced us to embrace cosmic inflation, a concept that now underpins all of modern cosmology. The story of the magnetic monopole is a perfect parable for the process of science itself. It is a testament to the power of a beautiful idea, the courage to follow it to its most extreme conclusions, and the wisdom to listen carefully to what nature tells you in return, even when what it tells you is silence. The unanswered question of the monopole remains a beacon. It continues to inspire new generations of physicists to build more powerful colliders, more sensitive detectors, to dream up new theories of unification that might tuck the monopole away in some yet unexplored corner of reality. Its potential discovery still hangs over physics as the ultimate prize, a Nobel-winning observation that would confirm a century of theoretical work in a single beautiful flash of data. But whether that day ever comes is in a sense secondary. The value of the quest has already been realized. The journey has already paid for itself 1,000 times over in the currency of knowledge, technology, and profound cosmic perspective. It reminds us that the goal of science is not always to find the thing you are looking for. Sometimes the most profound discoveries are made when you are forced to explain why it is not there. Sometimes the search for a single missing piece of the puzzle ends up revealing the breathtaking, unimagined structure of the entire puzzle itself. The monopole remains a ghost, but it is a benevolent one. It is a ghost that haunts us, not with fear, but with wonder, challenging us to keep searching, to keep questioning, and to never stop believing that the universe has yet more secrets to share. The search continues.